Why is quantum cryptography considered unbreakable by physics? Imagine a way to send secret messages that no one can ever crack, no matter how powerful their computers are. That's what quantum cryptography promises. It's a method that uses the strange rules of quantum physics to protect information. Unlike regular encryption that relies on complex math, quantum cryptography depends on how tiny particles behave. It's like having a lock that can't be picked because of the laws of nature themselves. The main idea behind quantum cryptography is called quantum key distribution. This process allows two people to share a secret key that keeps their messages safe. The magic comes from how quantum particles, usually photons, act. When someone tries to listen in or measure these photons, it changes their state. This change is like a red flag that alerts the sender and receiver that someone is eavesdropping. One key principle is called quantum superposition. It means particles can be in many states at once until measured. When an eavesdropper tries to check the particles, they disturb this superposition. This disturbance makes it obvious that the security has been compromised. Another principle is called the no-cloning theorem. It says you cannot make an exact copy of an unknown quantum state. So, anyone trying to duplicate the key without permission will fail or cause detectable errors. Quantum entanglement is also used in some quantum cryptography methods. When two particles are entangled, measuring one instantly tells you about the other, no matter how far apart they are. If someone tries to interfere with one of these particles, it affects the other, revealing the intrusion. The Heisenberg uncertainty principle states that certain properties of particles cannot both be precisely known at the same time. If someone tries to measure the particles, they inevitably disturb them, making eavesdropping impossible without detection. All these principles work together to make quantum cryptography incredibly secure. If anyone tries to intercept or alter the key, the act itself reveals their presence. The key is then discarded, and new secure communication can begin. This means the security is not based on how hard a problem is to solve with computers but on the fundamental laws of physics. Even the most advanced future computers, including quantum computers, cannot break this security because they would violate these basic principles. Quantum cryptography is becoming more important for protecting sensitive information in government, banking, and critical infrastructure. It's also paving the way for the future of secure communication networks, known as quantum internet. This technology promises to keep our information safe in ways that classical encryption simply cannot match. So, the reason quantum cryptography is considered unbreakable is because it's built on the unchangeable rules of the universe itself, making it a truly secure way to communicate.